Hello, everyone. Today, we will continue discussing some topics related to bipolar junction transistor. So in the previous class, we discussed the different applications of the bipolar junction transistor, and we agreed that if the transistor is working in the cutoff or in the saturation region, so in this case, the transistor can be used as a switch or in digital logic circuits. And we agree that in the active mode, if the transistor is in the active mode, so we can apply the relation I collector equals beta times I base. So in this case, the transistor will be in the active mode and it can work as an amplifier. And we could see how can we control that. Today, we are going to discuss something more in deep about the biasing of the bipolar junction transistor. So the objective is to investigate the various biasing schemes of bipolar junction transistor circuit, including bias stable biasing. So what the meaning of bias stable and what the meaning of stability in general. So we will discuss the meaning of stability of a BJT today. So let's start firstly with our common emitter configuration. So this is the single base resistor biasing. We have one resistor to bias our transistor in order to have a base current. So firstly, this is the main circuit, as you can see here. This is going to be AC, and you have here a coupling capacitor. So this series capacitor for sure will prevent any DC component coming from this side. So this circuit on the left-hand side here is representing the AC analysis, or we can use it if we are going to make AC analysis. However, for the biasing means DC analysis. So we don't care about the AC for the time being. So for the circuit we have on the left-hand side, even if this one is going to use for amplifier, firstly, we need to be sure that the transistor is working in the active mode. And this can be made by the DC analysis and check the biasing technique. So this is now the DC circuit. So assume that we have DC supply only. We don't have AC supply. If you apply superposition, so this capacitor and this supply will be removed from our circuit. And here VCC is going to be just DC component, as you can see here. In this case, we will have the IBQ, the quiescent point, the base current of the quiescent point, the collector current of the quiescent point, and for sure the emitter current will be flowing here, and the emitter is connected to ground. So this is called single base resistor biasing. Single base resistor biasing. And this is the first technique we will discuss today. What do you need from this technique? Actually, we need to achieve a certain quiescent point. Quiescent point means I need to have a certain operating point on my I collector and V collector to emitter characteristics. So if we have many curves like that, as you know, so which operating point will be used according to the load line. So this is here at different values of IB. I'm going to say this is IB1, or let's say capital, because this is going to be DC analysis. So IB, even capital B, not little b, okay, IB3. So at different values of IB, and we will design for sure what's called our load line. Let me draw the load line in a different color. So assume that according to the values we have a certain, the values of the RC and RB, we will have a certain resistance, RC and RB, to provide this load line. So what the value here and what the value here. We need to check that according to the parameters we have. And the intersection with our curve, the selected curve at IB1 or IB2 or IB3 will be our Q point, which is going to be our operating point for the amplifier, for instance, if it is amplifier application. We discussed also before the load line, just quick revision. So if you make the circuit equation, the output circuit equation here, so you have VCC equals I collector times R collector plus V collector to emitter. So this actually represents our load line here. At this point here, this point of intersection here, the collector current equals 0. So at IC equals 0, in this equation, you will find that the value of VCE equals VCC. So this means this volt here is VCC. And at VCE equals 0 in the same equation, so this means all the values of IC on this horizontal line. So this point here represents the value of VCE equals 0. So if you substitute that in our equation here, you will get that the value of I collector equals VCC divide RC. So we can say the value of IC is going to be VCC divide RC. So this means the value of IC here is VCC divide RC. So we could get from the load line the value of VCC and RC needed in order to achieve or create this load line on any transistor. So this is a basic step. In order to identify now the value of IB, the value of RB, you need to know what is IB needed. And this for sure can be obtained from our characteristic. So if you need a certain value of ICQ and VCEQ, so you can use the beta of your transistor and get the base current based on the ICQ. So we can say, after getting the values of RC and VCC, so we can say then the value of IB, the base current, will be IC divide beta, and beta is our transistor and should be defined as well. And from that, we can get RB from this circuit right here. So we can say the value of, or the waveform right here from this point to ground. So we can say VCC equals I base times R base plus the value of VBE on, which is 0.7 volt. So if you get the value of IB by means of collector current and beta, so it's easy now to identify the value of base resistor. So this is the way how can we identify the parameters in order to achieve a certain Q point for our BJT in this circuit configuration, which is single base resistor biasing. Let's solve an example together. So here, we need to design a circuit with a single base resistor. So if I said that in the exam, you don't need to have the circuit in front of you, because this is going to be the configuration of the single base resistor. So you have to memorize this configuration. So single base resistor means we have just one resistor connected from the VCC to the base of our transistor, and all of the time we will have one resistor connected from VCC to the collector, and the emitter is connected to ground. Now, we need to make this analysis here in order to achieve a certain Q point. So the example here says, or the objectives here is to design the circuit. Design means calculate. So the word design here, if I say design in any question, so this means getting the value of resistors. What resistors should we have in this circuit? So the specifications we have will be VCC equals 12 volt. So we know the value of the volt here. This is 12 volt. And the transistor quiescent points or values are ICQ is 1 milliampere. So we know the current here is 1 milliampere. And also VCEQ is 6 volts. So this is here equals 6 volts. So we know the current and VCE of this branch right here. So I think it's very easy now for us to obtain the value of RC, because we know now the value of VCC and IC and VCE. We know the value of VCC, the supply volt, IC, the collector current, and VCE, the collector to emitter volt. Let's start, guys, with the value of B equals 100 and assume the VBE on in our analysis to be 0.7. So in this case, we can see here on the output current voltage relation. So VCC equals IC RC plus VCE. So we can say 12 volt equals I collector is 1 milliampere. So 1 times RC in kilo ohm plus the VCE, which is 6 volt. So from here, guys, we can say RC equals 6 kilo ohm. So we got the value of RC from this relation. The second relation we need to use is the input side circuit. So from here, we need to know what is the value of R base. So we can do the same calculations as we mentioned, but firstly, we need to know the current I base. So if we assume using beta equals 100, so this means our I base will be I collector divides beta. So I collector is 1 milliampere divide 100. So this means 0.01 milliampere. So this is our base current, or 10 microamperes. So this is the base current we have right now. We need to get the value of R base. So simply we can use the output equation, the input equation side. So VCC equals I base, R base, plus VBE on, which is 0.7. So we can say 12 volt equals 0.01 milliampere times RB in kilo ohm. So we don't need to multiply times 10 to power minus 3 because in kilo ohms, so the resistance is multiplied times 10 to power 3. So the total now milliampere times kilo ohm, the result is going to be volt, which is balanced with the VCC 12 volt. So we are right now, plus VBE on, which is 0.7. So from here, we can say the value of R base equals 12 minus 0.7 volt divide 0.01. If you calculate this value, so let me calculate that with you, 12 minus 0.7 divide 0.01. So it's going to be 1,130, which means the resistance is, let me write it firstly in kilo ohm. So 1130 kilo ohm, or I can say 1.13 mega ohm. So this is the base current value. This is according to our calculations now and assumption of using beta equals 100. Okay. So here is the textbook solution, guys, as we already calculated. So we have 6 kilo ohm collector resistance. Base current is 10 microampere, 1.13 mega ohm base resistor. If we selected a certain transistor right now, you will find that this is our operating point here, the Q point. We have 6 volt VCE and 1 milliampere collector current. And we said that this is representing here VCC, and this here represents the value of VCC divide RC. So we said VCC equals 12, RC equals 6. So 12 divided 6 is 2. So this is the value of the current at 0 VCE here. And this is our load line. And for sure, the intersection of the load line with our operating curve or operating characteristic of the BJT is going to be our Q point. So here now, this curve, the selected curve here, represents the characteristic at IB equals 10 microampere. And actually, beta here will be 100. Okay. Now, regarding the stability of our circuits, what's the meaning of stability of our circuits? So in order to investigate the stability of this biasing technique, we just will assume something. Assume that the range of our gain, beta, is from 50 to 150. And see how big is the difference in IC and VCE. So we're going to assume that the current is IB, the base current is constant, 10 microampere, and investigate what will happen if the transistor gain beta is varying between 50 and 150. What will happen to the values of VCE and IC? So what we can do is we can repeat the calculations to get the equivalent values of IC and VCE at the 50 and 150 current gain. So you know that the equation VCC equals VCE, the collector to emitter volt, equals VCC minus ICRC. So 12 minus IC times 6. So 6 is the value of RC, so we don't change our circuit anymore. The circuit is designed, but we just need to check the stability of the circuit. So how much VCE we will have according to the IC. And take care that we said IB equals 10 microampere. So if IC equals 10 IB equals 10 microampere. So if IB equals 10 microampere, now what will be the value of IC in case of beta equals 50 and beta equals 150? For beta equals 100, we already calculated this in our question right now. This is our previous case that we already calculated, and we provide all of the values in this question right now. Let's see now what will happen if we change beta to 50. So if we have beta equals 50, so this means IC is going to be beta times I base, which is going to be 0.5 milliampere. And if you substitute here in our circuit with the 0.5 milliampere, this means 12 minus 0.5 times 6. So the result is 9. So VCEQ will be 9 volts. So this is my first operating curve. I'm going to say if I have beta equals 5, I'm going to draw another curve now. This curve will intersect with the load line, and VCE equals 9 volts and IC equals 0.5 milliampere. So this is my, or this is our curve. This is our new curve if we said that beta equals 50. Repeat again the same calculations at beta equals 150. So we will get that ICQ is 1.5 milliampere and VCE is 3 volts. So this is our operating point at beta equals 150. So this means this is our new curve or new characteristic if beta equals 150. What we have now is very big distance between the beta equals 50 to 150. And this can be concluded as follows. This biasing circuit is unstable to beta changes. Can you see, guys? You have a different or very high range of IC and VCE changes with a range from beta equals 50 to 150. So this is called now unstable. This is called unstable circuit. So this means we dislike this circuit and the amplifier configuration because, again, it's very sensitive to beta changes. And this is going to make the circuit unstable. Let's investigate another circuit topology. So in the circuit, you can see now here, this is the second circuit we have in our textbook. So this is called voltage divider biasing and stability. So voltage dividing or voltage divider biasing. So the voltage divider means we have a voltage divider on the base, and at the same time, we have a resistor connected to emitter. So this is emitter-based resistor circuit. This configuration here, guys, we will give it a name of resistor-based circuit. Sorry, resistor or emitter resistor-based circuit. So yeah, emitter-based or emitter resistor-based biasing circuit. So let's see, guys, how can we analyze firstly this circuit? So analyze means, I mean by the analyzing the DC analysis or make DC analysis for our circuit. So making the DC analysis again means getting the values or the relations of IC, VCE, IB, and the relation with the all resistors we have in our circuit. So in this topology, guys, if this is going to be our complete AC circuit, so again, apply superposition in order to make just DC analysis. And at the same time, we are going to replace this circuit by another standard circuit, which is the emitter-based one, but just using one resistor right here. So we will get the Thevenin equivalent circuit between these two terminals right here. So you know that when we apply Thevenin analysis, so we assume that this circuit will be removed and getting the V Thevenin and R Thevenin between these 2 points for our circuit. So our circuit here means this part of the circuit, guys, not the other side. We need this side right here. Okay. So how can we do that? How can we do that? Firstly, we will remove the AC. So the circuit will be just these two resistors, R1 and R2, connected to our circuit here. So what would be the voltage here between these 2 points? So we can say that the voltage between these 2 points is the volt across the resistor R2. So this can be obtained as follows. Apply voltage divider rule for this branch right here. So we can say that V Thevenin equals R2 divide R1 plus R2 times VCC. So this is the voltage divider rule applied here in order to get the Thevenin volts between these two terminals. Okay. And what is the Thevenin resistance for this circuit? So the Thevenin resistance between this circuit here, guys, applying superposition again means the AC will be removed and you know that when we get R we delete every voltage source in the circuit. So if this is my circuit here, we have two resistors like that. So these are the two terminals that we need to get R in between. And you have here VCC. This is R1. This is R2. So we need to get the resistance between these two terminals. So this VCC will be canceled. Cancel means connecting the R to ground. So this will be connected right here. So this means R is nothing but R1 parallel R2. So we can say R is equal to R1 parallel R2, which means R1 R2 divides R1 plus R2. So this is the equivalent of R Thevenin. Once we got R Thevenin, we can now substitute in the equivalent circuit of the circuit or emitter-based resistor circuit, as you can see here. So we have here again VCC RC, our transistor, emitter resistance connected to ground, and between these two terminals again, between the base to ground, we have our R Thevenin and V Thevenin. If you would like to make analysis now for this circuit right here, so we can say from the output side, guys, we still have the same equation. We don't have any change from the equation here. So VCC is still the same. VCC equals IC times RC plus VCE plus IE times RE. And you can replace for sure IE by 1 plus beta I base, and IC equals beta I base. So this is going to be the equation of the output right here. From the other side, so you can say that V Thevenin equals I base, this is the base current here, times R Thevenin plus VBE on, which is 0.7 volt, plus I emitter times R emitter. So let's see, guys, how to make the equations here. So I said here V Thevenin equals I base R Thevenin plus VBE on, which is 0.7, plus I emitter times RE. If you replace IE by means of I base, so you will have I emitter equals 1 plus beta times I base. So we can say now V Thevenin equals I base times R Thevenin plus 1 plus beta times R emitter. And all is added to VBE on, which is 0.7 volt. So from this relation here, if you move this to the left-hand side in a negative sign, so V Thevenin minus VBE on, and then divide over this complete term, so we can get the I base. So we can say I base equals V Thevenin minus VBE on, divide R Thevenin plus 1 plus beta times R emitter. This is I base, and we assume all of the time that transistor is working in the active mode. So we can say I collector equals beta times I base. So we can say now I collector is beta times IBQ. So it's beta times all of our equation right here. So this is the DC analysis of this equivalent circuit. Let's take a numerical example to see that together. So here in this example, we need to analyze the emitter-based circuit. So the example or the objective is analyze a circuit using voltage divider bias circuit and determine the change in Q points. So we will do the same, guys. So we will assume firstly B of 100, and we will see the effect of considering beta change from 50 to 150 and see if it is stable or not stable here with this configuration. So starting again here, guys, starting from the Thevenin circuit. So we have R Thevenin, as we mentioned, R1 parallel R2. So this is going to be 56 in parallel with 12.2. So here we have all the values. Let me calculate firstly here, guys. So we can say here R Thevenin equals R1 parallel R2, which is 12.2 kilo, parallel R2, which is 56, sorry, R1, 56 kilos. So this means 12.2 times 56 divide 12.2 plus 56. So we can get R Thevenin in kilo ohms from this relation right here. So if you do that, you will get value of 10 kilo ohms. Okay, so this is the first thing. Secondly, get V Thevenin. So we already drive the relation of V Thevenin right here. So V Thevenin is nothing but the voltage divider rule. So R2 divide R1 plus R2 times VCC. So we can say V Thevenin equals R2 divide summation R1 plus R2 times VCC. So this is going to be now 12.2 divide 56 plus 12.2 times VCC, which is 10 volt. If you do that, you will get the value here, which is 1.79 volt. Okay, so again, this is our V7. Now, put these values right here, R Thevenin and V Thevenin, and start doing the analysis. And again, since you know the analysis, you can make the formula sheet with you in the exam and use the equations. So since you already have the formula sheet and you can use this equation, guys, so please, I don't expect any mistakes in calculations or equations. Okay, since you already is allowed to use, you are allowed to use the formula sheet. So please, guys, I will not accept any mistakes in the equations. So now, here in our circuit, you know the relations. So these are the relations that we derived. So get the value of I base. So substitute in the equation V Thevenin minus VBE on divide R Thevenin plus 1 plus beta times RE. We have all the values, and we will assume beta equals 100 in the beginning. So this is now our number. So IB is 21.6 microampere. Calculate the I collector. So I collector equals beta times I base. So this is going to be 2.16 milliampere. And the emitter current is nothing but 1 plus beta times IB. So it's going to be 2.18 milliampere. And VCE can be calculated now from our circuit here. So if you apply the Kirchhoff here in this circuit, you can say VCC equals I collector RC plus VCE plus I emitter times RE. For sure, you can use, instead of IB and IC and IE, you can use beta and IB. Okay, but you already calculated everything. So you have IE, you have IE, you have IC. So you can substitute now in this equation in order to get the value of VCE. So you can say now VCE equals VCC minus IC RC minus I emitter RE, and you can get the value of VCE, which is 4.81. So now we got all the values of our Q points. So again, the value of Q points are VCE and IC. Why? These are the values that, and IB as well. So these are the values that we will use to select your operating curve of your BJT. Now, after getting the Q point, we need to check the stability of this circuit to the change in our current gain. So we will do the same. Make the calculations again for beta equals 50 and beta equals 150. If you do that, here in our circuit, you will find these values. So if if you compare the different values of IB, you will get these different values. So these are the values of IB. If you compare the values of IC, you will get these different values of IC. Take care of that. In the first case, this is important note here, guys. So here in the first case, in this comparison, if you have a look here, you will find that we compare at constant IB. Why? Because this circuit configuration will not allow a change for I base. Whatever happening for beta here in this side, so I base will be the same because you have a fixed resistance and VCC value. And VBE is 0.7 all of the time. So there is no change happening in IB. But here in this circuit, guys, let me get it here from here firstly. Yeah, from the relations here. So IB, what is the value of IB? Can you see here, guys? IB already is beta dependent. So it depends on the value of beta. So this means you have to change as well the value of IB in this curve or in this circuit. So with different values of beta, you don't have constant IB. You have to repeat the calculations for all the equations. So you have to calculate IB, you have to calculate IC and VCE. You have to calculate everything here once you need to get the change or the effect of beta. Again, it's just direct substitution in the relation. So getting V7 firstly. So as you could see here, guys, V7 is independent of beta. R2 divide R1 plus R2 times VCC. And R7 is the same. It's independent of beta. So these two values will be the same. These two values will be the same. However, for our circuit right here, the value of I beta will be different, not because of R7 or B7, but because RE and IE are a function or dependent variables for the value of R7. And let's say RE is constant, but IE is still a variable in the relation. So IB will depend on the value of IE in this circuit configuration. So you have to use the relations to get all of the values. So again, we need to calculate IB, IC, and VCE for the three different cases. We already made the calculations at beta equals 100. So repeat the calculations at 1 and at 50 and 150 beta. Now, what we can see is you have minor changes in the values of IB, VICQ, and VCEQ. And as you can see here, guys, if this is the first curve, second curve, third curve, so you have very limited changes, which means we can conclude here that this biasing circuit is more stable to the changes of beta. So including an emitter resistance, RE, has tended to stable Q points. So this is the conclusions that we can get from this configuration. Okay, guys. So today we learned two techniques for biasing our BJT. First technique is the first circuit we mentioned here, which is single base resistor. The second technique is the voltage divider technique, or the voltage divider resistor, along with using R emitter. And we could find that the first circuit is not stable to the change in the current gain beta. However, the second circuit is stable to the changes in the current gain beta changes, okay? And if we use the emitter resistance in the circuit, so this will keep everything stable. So this is our class today. So as a summary, we learned the DC analysis, biasing circuits, the voltage transfer characteristic we already learned and discussed in the previous class, guys. So we learned the DC analysis circuit also not the application. This has been learned in the previous class. So we learned the biasing techniques of the BJT, and we learned also the stability of BJT with beta changes. So this is a summary for what we have discussed today. Thank you so much and see you in the next class.